Okay, chapter 12. I hope you guys all were able to again find the notes. Let's go ahead and get started. This will kind of pick up on what we talked about in chapter 10, kind of extending some of those concepts of probability. And here at the beginning of the notes, I know it's been a little while. You guys have been studying for the exam. I wanted to kind of refresh you on what we talked about, sort of the idea of probability and kind of where we came from and where we're going here in the class. So again, if you remember the first part of the class, and this was chapters 1 through 6, we did things like exploring the data, exploratory data analysis, where we looked at displaying data, describing data. That was chapters 1 and 2, maybe even a little bit of 3 in there. Then in chapters 4 and 5, we looked at 4, 5, and 6. So this is also chapters 8 and 9, I guess. In chapters 4, 5, and 6, we looked at exploring relationships between two variables. So we looked at scatter plots, we looked at regression, two-way tables, and then we talked briefly about how we would collect good data. And later in the course, just keep in mind, keep reminding you here that the goal of this course is that we're going to do inference, which is drawing conclusions about our population based on some information that we collect. So chapters 8, we talked about how we get a good sample, and now we want to think about how can we use information we get from that sample to talk about the larger population. So just a heads up that's where we're going, and just then remember that probability is kind of our connection between these two sections, these two concepts, these two ideas, and that's where we're always trying to obtain a representative sample or a random sample, because then the rules of probability allow us to make that generalization from our sample to the population. So that's all things that we've seen before. And then just remember that the idea of probability, and that the reason that we want random samples, and these in chapter 9 we talked about randomizing our treatments, randomizing our experiments, is because this idea about chance behavior, the idea that it's unpredictable in the short run, but nonetheless has a regular and predictable pattern in the long run. So what we talked about on Friday was that idea of how many women are sitting in your row, and if you had more and more people in your row, it would eventually get close to 50% women. Another example that I wanted to quick show you was this example of flipping a coin. So suppose I flip a coin 10 times and I get that sequence of heads and tails. So I get a bunch of heads first, I get a tail, a few more heads. So out of these 10 tosses, what proportion of heads do I have? Just out of these 10 tosses. Yeah, if you count them up, I have 7 out of 10, or 0.70%. So out of 10 tosses, again, I've done this 10 times. And the other thing I can do down here, I can also plot the number of tosses I have and versus the proportion of heads. So here at the first toss, I got a head. So 1 out of 1 was a head. Second toss, I also got a head. 2 out of 2 were a head. All the way up to the 5th toss, I got 5 out of 5 heads, so I have still 100% of heads, and then it starts to go down. Why do I have that red line? Why do I have that red line in the middle of the plot? It's 50%. Yeah, so that's what you would if you just sort of think eventually I should have about 50% heads and tails. So the thing is here, I've flipped a coin 10 times. And I am getting some kind of strange things. For a while I have 100% heads, and eventually here at the end I have 70% heads. So again, kind of thinking about that same idea about number of people in your row. If I did this lots of times, so if I did this instead of 10 times, if I did this 1,000 times, I can do the same plot down here. I can do the number of tosses versus the proportion of heads, and you can see that eventually we get out in here, we get to be about 50% heads. So going back to that idea of chance behavior, so this is an example of a chance behavior, flipping a coin. If I just do it once, I don't know what's going to happen. I might get a head, I might get a tail. So that idea that it's unpredictable in the short term. So up in this area from tosses 0 to, I don't know, maybe 100. It's unpredictable. We don't know exactly what proportion of heads we're going to have in those early section of tosses. But once we get out here to tosses 400 to 800, 400 to 1,000. Well, there we have a very predictable thing, right? We knew that coins should give us heads about 50% of the time, and so if we do that 1,000 times out here, at the end, this is very predictable. So just that idea that, again, that in the short term, if we have a chance behavior like this, in the short term it's unpredictable, in the long term it's predictable. And what we're going to use is we're going to use that it is eventually predictable. This is going to tell us about probability. So kind of whatever that regular pattern eventually becomes, that's kind of, you can think about, that's the idea of probability. So that from this we could see that getting the probability of flipping a head is indeed about 50%, or 0.5. So we're going to use that regular and that predictable pattern in the long term. That's kind of going to be our idea for how we talk about probability, or what you would expect to happen is kind of what we're going to use for probability. Any question you guys can think of on probability? Is the idea kind of the basic idea getting through? Okay. Well, we'll do some examples here and kind of keep getting at these ideas again and again. So now we're kind of going to move into the general case. We're looking at some other examples, and what we're going to use a lot, and as we work through these examples, is the idea of a Venn diagram. Have any of you guys heard of or used a Venn diagram before? Yeah, many of you. Okay. So just again, I keep hitting on the fact that this is, that pictures are very helpful for me in this class, and I think they can be a good way to visualize what we're trying to do. Venn diagram is another way to draw a picture to represent a certain problem. And so so these diagrams are going to be helpful when we're asking questions about probabilities. So the first example that I have here says here that if we took a sample of 1,000 people, if we have 88.7% of them are right-handed dominant, so are right-handed, 47.5% of them are female, and 42.5% of them are female and right-handed. So they're both female and right-hand dominant. So if we want to draw a Venn diagram for this situation, here's how we would go about doing that. So as you might remember, Venn diagram involves these two circles, and then you want to make sure to enclose them with a box. And kind of as we're setting this up, I want to be very clear about my notation. I'm going to use a capital R to equal to represent right-handedness, and I'm going to use a capital F to represent female. And then so I want to label, again, I have two circles here. I have two conditions. I have your handedness and your gender. So I'm going to label this one R and this one over here F. So that the circle with the R on it corresponds to people who are right-handed. Circle with the F corresponds to people that are left-handed. Okay, so this is my Venn diagram that I have for the situation, and we can start filling in some numbers here of what these situations actually are. So first of all, what's one number that I can fill in on my Venn diagram here? Can anyone help get me started? Yeah.
42.5 goes in the middle because it's female and right-handed.
Okay, exactly. So we can pick out the 42.5%. Those are people that are both right-handed and female. So that's going to go in this little part of the circle here, because that that part of the diagram represents people who are both right-handed and female. So let's go with a decimal here. This is 0.425. And so then what's the number that goes in? What are some of the other numbers that you can fill in up here? Yeah.
47.5 for females.
Okay. Yes. Exactly. So what I know that I have 47.5% of my people are females. So that means everybody inside this red circle is going to be 47.5%. So I want to kind of split that apart. So the part that will go. Let's see if I can just erase that. So what part goes? What number goes inside that part of the circle, or what does that group represent in this. My eraser's not working. So what does this shape represent? I think I heard you say it.
Female left-handed.
Right. So that shape represents females that are left-handed. So we do have 47.5% females, but we already have 42.5% of them in that small shape. So this is not to scale. So what number would go in that sort of half moon shape? Yeah. Yeah, exactly. So we have just 5% who are females and left-handed. So and this number comes from, this is 0.475. All of our females minus just those that are right-handed, because we want only the left-handed females there. All right. So how about my last sort of shape over here? What group does that represent? First of all, right-handed males. Exactly right. So what percent of my sample here is right-handed males? 0.462. Yeah, exactly. So 0.462, and again, this comes from taking all of the right-handed people we have, 0.887, and subtracting off the 0.425 who are females. So I have 0.462, 46.2% of my people here are right-handed males. So are we done? What group have we left out here so far? You've left me out, by the way. So what group is not up here? Left-handed males, exactly right. So how many left-handed males do I have in my sample? All right. So how many left-handed males do we have in the sample? Or how are we going to get there?
You add up all the percents inside the two circles and then subtract it from one.
Exactly right. So we want to add up. Again, we have to have 100% of our people in here. So if we add up the numbers inside the circles and subtract from 1, it's exactly what we're going to do. So the number that goes in here is going to be 1 minus, and we can take 0.462 plus 0.425 plus 0.05. And if you calculate that out, that should give you 0.063. So that's how we can fill in the Venn diagram to sort of split our people into all the different groups that we have. And again, you just kind of have to reason out what each part of each circle represents, and then you can fill in those numbers there. Okay, so and any questions on what I'm doing here? Does that make sense? All right. Well, the reason that we went through all that song and dance was that so we can make some of these questions a little easier to answer. So again, 0.063. All right, just filling in. Again, this is right-handed. This is female. So now the question that I might want to ask is, calculate the probability that a randomly selected person from this sample is right-hand dominant or female. So again, remembering that that R is right-handed, F is female. What I want is the probability that a randomly selected person, my notation here is going to be, well, let's write it out. I want the probability that a person is right-handed or female, which in my notation I'm going to write P of right-handed or female. And just to remind you that that capital P with the parentheses, again, that's just going to be our notation for saying the probability of. And then inside the parentheses, we'll put whatever we're interested in. So we want the probability that a randomly selected person is right-hand dominant or female. We can represent that with P, parentheses, R or F. So we want right-handed or female. And so, again, using the Venn diagram, you can now pretty quickly see the number that we're looking for. You can kind of add them up. But in general, the way that we can do this is going to be equal to the probability of being right-handed plus the probability of being female. But now I need to subtract off the probability that they are both right-handed and female. So this goes back to that, sort of goes back to what we talked about in chapter 6 when we were talking about from the 2A tables, what percent of my people are something and something or something else. This is kind of that or question. We have a or floating around there. So we can now see what each one of these things are. Again, from the information we were given, the probability of being right-handed was 0.887. Writing too big up here. So this is equal to 0.887 plus probability of being female was 0.475, and then we subtract off the part that's the same. And that is going to give us 0.937. And just had a note on the back channel. I did maybe that 0.63% represents more than just right-handed males. That was a good point. Thank you. So again, this is sort of my general way. But if I want to use my Venn diagram here, also note that I could just add up these three numbers, and that would be the exact same thing. So if you go about making the Venn diagram, again, I want people who are right-handed or female. I can just add up everyone that's inside those two circles. So maybe just a quick question is why do I subtract off the probability of being right-handed or female, right-handed and female, excuse me. Exactly. So we counted them twice. So the 0.425 is in 0.887 and 0.475. So we don't want to. We have to make sure we don't count those folks twice. So this here, what we've just done is an example of the general addition rule. So for any two events, A or B, whatever those will be, what we often use to describe just an arbitrary event, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And again, the question that why do we subtract off the probability of A and B in the general addition rule? We just said that again because again the probability of A and B, it was counted once with probability of A, and again with the probability of B. So we double counted, and we need to subtract that off. So I just had a comment came in, an excellent comment come in that says, we go back to our Venn diagram. Now that we have it all drawn out, why not just subtract 0.063 from 1? Absolutely, that is a great idea. That'll give you the exact same answer. And actually, getting a little ahead of us, we'll have a rule to talk about how we can do that. So that is exactly right. That's another way to do the problem. And I'll say more about that in just a second. So thinking about real quick, kind of that was our general case. But if we go back to chapter 10, what we saw right at the end of that chapter was something a little more specific. And that was the case that what if there's no overlap between A and B? So what if these whatever two events we're talking about, what if they have nothing in common? So our definition in that case will be that events A and B are disjoint if they have no outcomes in common. So if A and B sort of can't happen at the same time, we're going to say that those two events are disjoint. So then what does the Venn diagram look like when A and B are disjoint? The Venn diagram would be two separate circles. So over here is A and over here is B. Again, they have nothing in common. So we're going to kind of show that by separating the two circles and saying that they have no overlap there. So in that case, what does that mean for the general addition rule that we just looked at? So what happens to the probability of A and B when A are disjoint? When A and B are disjoint, the probability of A and B, what's that going to equal? If they can't happen at the same time, what's the probability of A and B? So we want the probability of A and B here. So that was the probability of A or B. So you're getting just ahead of me a second. So what's the probability of A and B if they can't happen at the same time? Yeah. Okay. So that's the probability of A or probability of A or B would be the probability of A plus the probability of B. So getting just ahead of me, that's the next thing I'm going to write. But what is this probability? Probability of A and B if they can't. So if my Venn diagram looks like this, the probability of them both happening is 0. Thank you. So the probability of A and B, if they're disjoint, is 0, which, as you guys were saying, so what that means is that the probability of A or B equals the probability of A plus the probability of B. Again, in general, it equals A and B. But now this part equals 0, so this is going to be equal to probability of A plus the probability of B. So I think that's where you guys were going. I wanted to make that clarification first. Thank you. So again, we have our general addition rule, which is this statement right here. But in the special case, when A and B are disjoint, then it simplifies down to what we saw in chapter 10. So if your Venn diagram looks like it did on that previous slide, where the two circles are totally separate, you can simplify the rule to look like this. So again, talking the general case and then a more specific case here. So going back to our example, what about the probability that a randomly selected female is neither right-hand dominant nor female? So again, the first thing I want to write out is what am I asking for? Keeping an eye on the Venn diagram, I want the probability of neither right-handed nor female. So again, just taking what the problem says to me there. So who can give me a hand? How am I going to go about finding what this answer is? or I guess, so what's the opposite of the group that I'm interested in? So if I'm interested in those people that are not right-handed nor female, what group is that? Exactly. So it's left-handed males or other categories within here that we don't put. So again, this is equal to the probability of think about this is equal to the probability of being left-handed and male. So we can get to that by subtracting off all those people that are left-handed or female. So we can, or sorry, right-handed or female. And so then what this will equal is, again, we can take what we found previously. This is 1 minus 0.937, and that's going to give us that part that was in just floating around in the box out there. So this is an example of what the comment that came in a few minutes ago was, that why don't we just subtract 0.063 from 1? And this is this general rule down here. So if you want the probability of the opposite of something happening, again, it's just we're going to take 1 and subtract off the probability that it does happen. So we saw this at the end of chapter 10, just a refresher that this can be a very good way to calculate probabilities, as this person suggested in the previous example. So this is what we're going to call the complement rule. Just that the probability that A does not occur, some event A does not occur, is just 1 minus the probability that it does occur. Okay. And finally, calculate the probability that a randomly selected female is right-hand dominant. So again, I want the probability that a female, that a randomly selected is right-handed. And the notation that I'm going to use here, this is, and I'll explain this a little bit more on the next page. But I want the probability of a person being right-handed, given that they are female. So I'm going to use that horizontal bar to represent a conditional probability, kind of like we saw back in chapter 6. So again, if I'm taking just the females in my group, who can help me get started on this probability? What is this going to equal? So of the females, what percentage of those are right-handed? Would be another way of asking the question.
42.
Yeah.
Would it be the 42.5% of females who are right-handed over the 47.5% of participants who are female?
Absolutely correct. Yeah. So again, kind of going back to that idea of who's the group that we're talking about here. So we're talking about females. So of the 47.5% of females that we have, 42.5% of those are right-handed. So that is exactly correct. And this is equal to 0.8947. And again, just thinking about what we wrote down here, what we wrote down was the probability of being right-handed and female. That was our 42.5% divided by the probability of being a female. Again, the probability of being a female in this group was 47.5%. Probability of being both right-handed and female was 42.5%. So take the ratio there to tell us how many females are right-handed. Exactly right. So just again to remind you that I've slipped some notation in here, that this horizontal bar here is we're gonna read, when we read that, it's gonna read given. So again, the probability of B with a horizontal bar A, this is a conditional probability now, and that we can read that as the probability of one event B, and the probability of event B happening given that the event A has occurred. It's kind of what our terminology is again. So probability of B with a bar A, we're going to read it's the probability of B given that A occurred. And again, kind of like our intuition was, that's just if we kind of take just the situations where the event A occurred, we want the probability that B also occurred. And so this leads us to another sort of definition here. This is what I wrote out on that previous page. As long as the probability of A is not 0, this is our definition for a conditional probability here. So the probability of event B happening given that an event A already occurred is the probability that they both occurred divided by the probability that A did occur as well. So this is I believe our third formula here. We had our general addition rule, we had the complement rule, and now we have our formula for a conditional probability. All right, so let's do this one more time here. So now let's calculate the probability that a randomly selected right-handed person is female. So again, I'm going to have a conditional probability, and which letter goes on which side. So I want the probability that a right-handed person is female. F on the left, R on the right. Exactly correct. So F on the left, R on the right. So again, read that. That says we want the probability of being female given that you are right-handed. So in the wording of the problem, it's kind of the other way around. But thinking about what am I assuming is true. So what goes here is what am I assuming And so here we want the probability that, I'm assuming that I've selected a right-handed person, so then what's the probability that they are also female? This is our notation for that. So now if we want to find what this probability is, we know what our formula for this is. It's the probability of being right-handed and female divided by the probability of being right-handed. And a way to remember this is whatever's in this box is what goes in the denominator. So whatever comes after the given sign is what goes in the denominator. And now we can just fill this in. We know that the probability of being right-handed and female is again 0.425, but now all right-handed people are 0.887. If you calculate that out, it is 0.4791. Everybody okay with that? Again, maybe the big step is getting it written out in our notation, and then we know exactly what our formula tells us to do there. So again, just to remember, this is kind of exactly like what we talked about in Chapter 6, but what's the difference between those two conditional probabilities? Probability of F given R, that was, we assumed we had a right-handed person. And the probability of R given F, we assumed we had a female. So kind of like when we were looking at conditional probabilities in Chapter 6, the question to ask is, or sort of what group am I interested in? So am I interested in all the people that are right-handed, or am I interested in all the people who are females? And then I can calculate probabilities that way. So the wording on these problems can be very tricky. So just kind of read carefully and think about who is my group of interest here. Who is the larger group that I'm interested in, and that's going to be what goes on the right side of the horizontal bar there, the vertical bar rather. Okay, moving on here. So occasionally you'll come across problems that sort of embed these conditional probabilities into the question. So think about this question here. An A.C. Nielsen study found that 81% of households in the United States have computers. Of those 81%, 92% have internet access. So calculate the probability that a randomly selected U.S. household has a computer and has internet access. So let's set up some notation here. We're going to let C equal the event that the household has a computer, and we're going to let capital I represent the household has internet. It's kind of setting up what my notation here is going to be. And so what do I want? I want this says calculate the probability that a randomly selected household has a computer and has internet access. So I want the probability of C and I. So that's where we're going. So what are these two numbers that I've been given? So I have two probabilities here. One of them is 0.81 and one of them is 0.92. So who can tell me what those are the probabilities of? So start with 0.81. What is that the probability of? A little louder. Yes, probability of C. So again, probability that a household has a computer. So that's the probability of C. We're told that that's 81.81. So then the one that's a little more tricky is what is 0.92? What is that probability? Say again?
I/C.
Is it I with a bar C? So that would mean the probability of having internet given that you have a computer. Exactly right. So that's the probability of I with a bar and then C. So again, of those people that have computers, so again, assuming that C is true, what's the probability that we have, that the household has internet? So now we have some information that we can use to find what we want. So remember that the probability of, in general, A given B equals the probability of A and B divided by the probability of B. So what that tells us is that the probability of A and B equals the probability of B times the probability of A given B. So kind of moving those terms around there, we can solve that first equation for the thing that we want. So here the probability of having a computer and having internet, we can shuffle this around. This is equal to the probability of having a computer times the probability of having the internet given that you have a computer. And that is 0.81 times 0.92, which is equal to 0.7452. Perfect. So the key is there that we've slipped in a conditional probability in the statement of the problem. So you want to just be very careful about what the information has been given to you, and what kind of how we can use that to figure out what we want. So this is our fourth and I believe final rule here for probabilities in this chapter, and this is what we're going to call our general multiplication rule. And so if we want the probability, so this is what we're going to use to answer questions about one event and another event happening. So the probability of A and B is going to be equal to the probability of A times the probability of B given A. But again, we could do this the other way around like we did on that previous page. This is also equal to the probability of B times the probability of A given B. So whichever information you're given is what you'll need to use to answer this question. So sorry, this line shouldn't be in here. So this is our fourth general rule that we have here, and this is what we can use to answer questions about one event and another event happening. So just like for our general addition rule, we had a special case, so it sort of simplified if A and B were disjoint, right? Then it could just be probability of A plus the probability of B. We're going to have a special case here for our multiplication rule as well. So this is a definition here as well, that we have two events, A and B are independent if the probability of B given A is equal to the probability of B. So again, what this side says is this probability that B happens if A also happens. Sorry, let me rewrite that. Probability that B happens assuming A has already occurred, and this is just straight up the probability of B. So if these two things are equal, so if I assume that probability of A happens, if that doesn't change the probability of B happening, that's kind of what I mean by independent. These events sort of have no effect upon each other. So if A and B are independent, again here independent means they have no effect upon each other. So when that is the case, so when two events have no effect upon each other, then we're going to say they're independent, and then this identity will be true. And as yeah.
What's the difference then between independent and disjoint?
Okay, very good question. So what is the difference between independent and disjoint? That's a very good question. So in general, let's go back here to this definition here. So here's I think the way to see what the difference is. So if they are independent, then we can take this rule, come down here, and say the probability of A and B is equal to the probability of A. But now if they're independent, the probability of B given A is just the probability of B. So that's kind of our simplification to this rule. Is if they are independent, you can rewrite it like that. And so again, what did we find that probability of A and B was equal to if they were disjoint? Well, that probability was 0. So this is the difference there. I guess disjoint just means they can't happen at the same time. And independence is sort of a different. We're thinking about it in a different way. So And I guess my mathematical argument here is that unless one of those probabilities is 0, they won't be the same. And so that actually might be one of your homework questions, is like, can events be both disjoint and independent? And there you go. Great question. Okay, so let's try to use this idea, show you what I mean by independence. Maybe we'll finish up here with this example. Maybe we'll get through a little bit more. But suppose that my example now is thinking about blood types. So suppose, as we all know, someone with type O negative blood is considered to be a universal donor. So anybody, when you're receiving a blood transfusion, you have to match up on your blood type. But if someone has O negative blood, then anyone can receive their blood. So according to the American Association of Blood Banks, 39% of people are type O negative. So we have 2 unrelated people we're going to say are selected at random, and we want to calculate the probability that they both have type O negative blood. Okay, so let's again set our notation. Let's let O equal someone having O negative blood. And again, the probability that I'm interested in here is the probability that 2 unrelated people have O negative blood. So I think whenever you're working on if you're in your homework problems, if you're looking at a question involving probability, write it out. Write out what I'm interested in, just in plain words like I've done here. So I want the probability that 2 unrelated people have O negative blood. And then we can sort of start to put that into a framework that we know how to work with. So using those rules that we've talked about, how can we move into how can we get it into a form where we can use one of those rules? So what this is equal to, this is the probability that again, the first person has O negative blood, and the second person is O negative. So again, to try to put it in a phrase that's using things like and or the conditional bar, any of those things. And so if I use my notation here, this is the probability of someone having O negative blood and someone having O negative blood. So I'm going to use my special case that my independence rule. So why am I able to use the independence rule here? What am I saying about my first and second person here? Right, they're unrelated. They don't have an effect on each other. So again, because I've said 2 unrelated people. So for example, think about if we're talking about me and my brother. Would our blood types be related to each other? Would they be related? Absolutely, right? We shared some genetic makeup. But if you take me and one of you guys in here, when we don't have any family relations, whatever my blood type is wouldn't have any effect on what your blood type is. So that's kind of the idea here, is we just take 2 unrelated people. Their blood types will sort of have they won't have any effect upon each other, and we can say that they're independent. So this is just equal to probability of O times the probability of O, which from the example here, we know that 39% of people have type O blood. So this is just 0.39 times 0.39. 0.1521. So if you take, well, let me make another note. So here we've said we have 2 unrelated people. You might also see in your homework problem something like if we take 2 randomly selected people. So kind of that idea that if we randomly select people, they should be, if I've just randomly selected them, we could think about them as being independent. So that corresponds between randomly selecting and two things not having an effect upon each other. That's some language to look for there. So again, my probability of having two people that are unrelated, of both having O negative blood, is about 15%, 0.1521. Any questions you guys can think of on what we've covered here in Chapter 12 so far? General rules, what I'm doing here, notation, anything like that? Okay, great. Well, we'll finish up this section of notes on Friday and probably move on from there as well. So stay tuned for more notes being posted hopefully by tomorrow. And have a good rest of the day, you guys. Thanks for being here.